EEA, as part of the activities, is glad to organize the second lecture in Tech Talk series, where we invite notable contributors and speakers in the field of electrical engineering to give the talk about their works. Dr. Aniruddhan is an associate professor in the Integrated Circuits and Systems Group in the Department of Electrical Engineering at the Indian Institute of Technology, Madras. He had obtained his BTech degree from IIT Madras in 2000 and his MS and PhD degrees from the University of Washington in 2003 and 2006 respectively. Between 2006 and 2011, he worked in the RF analog group at Qualcomm, where he designed integrated circuits for cellular RF applications. He has been at IIT Madras since 2011, where his research mainly focuses on RFIC design. Now I would like to welcome Professor Aniruddhan to give a talk on the topic CMOS RFICs for full-duplex wireless communication.
And thanks to all of you for coming to the second series. How many of you attended Professor Radhakrishna's talk a couple of few weeks ago? Okay, so many of you attended. So this is kind of related to that work at a high level. So you will see, I think in the initial slides, you will see some overlap between this work and that work. Okay, so this is the outline of the talk for today. So I'll first, in a few slides, I'll introduce the concept of same channel full duplex. Those of you who attended Professor Radhakrishna's talk would already know a little bit about this, but this will serve as a refresher. And then the main portion of the talk are these two pieces of work by my MS and PhD students. One of them is a full duplex receiver based on a 2-antenna system without an LNA. The second one is a single antenna full duplex system with a specific way of achieving isolation between the transmitter and the receiver. But you'll learn all of these things when I go through the first few slides. And I'll kind of end by having a couple of slides on future directions, what can be done in the future. Okay, so if you look at conventional transceivers, the idea is very simple. You have two wireless nodes, each of them having a transmitter and a receiver. You have two-way communication. There is attenuation through the air, through the medium. So you put out a lot of power at your end, right? By the time it reaches the remote receiver, it's very small due to various reasons. Obviously, many of these antennas are isotropic, so they kind of radiate in all directions. That already gives you some, right? Radiation over a surface area of a solid sphere. So it will go down very quickly as 1 over r squared. Apart from that, it so happens that you also have multipath, fading, all atmospheric absorption due to various molecules in the air and so on. So there is a modeling that goes into the channel to figure out how much power you need to put out at the transmitter at your end to be able to give a small enough signal at the remote receiver. And of course, if you have two-way communication, you expect the same thing from the other side as well. Okay, and I guess about 20 years ago, almost 20 years ago and before that, the general consensus, the general idea was that you can't transmit and receive, right, at the same time and in the same frequency band for obvious reasons, right? You are trying to receive an extremely small signal. You are transmitting, putting out a very large signal, right? If you do it at the same time and in the same frequency band, you are going to pretty much see only your transmitted signal, right, and not your received signal. Your received signal is going to be buried under the huge transmitted signal. That was the basic idea. So if you go to the history of wireless comm over the last century and more, right, you will see that this block here, I have called it a duplexer here, right, but there is a block here that always performs the function of separating out the transmitter and the receiver in either time or frequency domains, right? If you look at a time domain system, you need a switch with sufficient isolation, right? You turn on one, you transmit. You open this, you turn this on, you receive. You do this, right, at whatever way you want. The other way to do this is the duplexer. It's basically a filter. You have a transmit spectrum, piece of spectrum. You have a receive piece of spectrum. you separate them in frequency, you now need a filter. You now need a very strong filter to filter out the transmitted signal at the receiver, right? So the insertion loss in this part needs to be very low. So you put in the filter, but whatever power you put in, very little should be dissipated in the receiver, in the filter. None of it should go into the receiver, most of it should go into the antenna. That will give you best transmit efficiency. On the reverse path, you want to get as much power into the receiver as possible without adding noise, without adding loss, and so therefore the loss of this filter needs to be as low as possible, and it needs to give, none of the power needs to go in here. So that's the basic idea, okay? And based on these two systems, you can broadly characterize almost any wireless system in today's world, right? Cellular, wireless, LAN, Wi-Fi, Bluetooth, whatever you take it, right? Whatever you take, it can be kind of classified under one of these two, okay? And so about 15 years ago, people started looking to see whether we can break this particular restriction. So what you need is a new duplexer, but the basic concept is very simple. You need a block here that allows you to transmit and receive at the same time and in the same frequency band. So question is, what do you need here, right? So broadly what you can say is that this block here, when you're transmitting, it should have very little loss in this direction. When you're receiving, it should have very little loss in this direction, okay? And there should be as much isolation as possible between these two, okay? Now, it turns out that if you actually write down the S parameters of this block, 3-port S parameters, it ends up being a non-reciprocal block in some sense, okay? So you cannot do it using linear elements. So it turns out there is indeed a block that does this, that's called a circulator. It uses a ferrite core. It is a, it's not a normal, of course not a linear, it doesn't operate linearly. Okay, there is indeed a block called a circulator. It is big, it is bulky, right? I'll show that in the next couple of slides and why we need something else to replace that. What is the advantage of doing this? It should be pretty obvious, right? Imagine at all instants of time you could receive at full bandwidth, right? Instead of just half the time, let us say, right? Your throughput just got doubled. Or you had previously allocated separate spectra, pieces of spectrum for transmit and receive. Now you can just reuse the same thing, you just double the number of users, double the available amount of bandwidth. So if you see conceptually at a very high level, there is a lot of advantage and it's huge, okay? It's huge because normally the dependence of things like bandwidth on number of users, etc., on, for example, power consumption. You may think that, hey, what happens if I burn power here? It is a non-linear dependence, it's not a linear dependence. Even if you end up burning extra power, right? Even if your noise increases a little bit, it may be a perfectly acceptable trade-off, okay? Because if you try to burn power in a traditional system to achieve the same doubling of throughput, etc., it is not just linear, okay? So if you had to just double the amount of transmit power, for example, it would be acceptable. That's what I'm trying to say, okay? Okay, so quick, I'm going to put some numbers here, okay? There are some numbers coming up also. I may not in every instance tell you how we came about those numbers. You'll have to trust us. But if you go pick up the standards documents, you will see, you'll be able to calculate these numbers yourself. If you take a wireless LAN system, right? Wireless LAN system is easy because short range communication, right? The shorter the range of communication, the lower the transmit power that you need to put out to reach the remote person. Also, the larger the receive power, because you are also closer to that person, the dynamic range between the transmit and receive systems comes, receive signals comes down. From that point of view, the shorter range communication systems works out better. But you have a problem, right? Many short range communication systems are also low bandwidth. You don't have a need to double the bandwidth. If you have Bluetooth, for example, there is a data cap, okay? It's a few megabits per second. Okay, you don't need more than that because it's not meant for that. Right? It's not necessarily meant for high bandwidth, hundreds of megabits per second or gigabits per second type of communication. Wireless LAN on the other hand is. It happens to be relatively short to medium range. It's also high bandwidth communication. Okay? So there is indeed a requirement here. If you look at these numbers, so the average transmitted power in the wireless LAN standard is about plus 20 dBm. Okay? The weakest desired signal that you need to receive is about minus 80 dBm. Okay, which means there is about 100 dB dynamic range between the transmit and the received signals that you want to separate out. Makes sense to everybody, right? So, if you went to a system like cellular, right, LTE for example, this number would jump up, right, by another 20-30 dB at least. Okay, because the transmit power would not be 20 dBm, it will be plus 30 dBm. Okay. The receive sensitivity would not be minus 80, it would be more like minus 95 or minus 100 dBm. Okay, so automatically these numbers would just move apart if you move to a longer range communication system. Okay. Why do you need to cut out this? It's obvious, right? If you are trying to transmit something 100 dB above, your receiver would just saturate, right? You would not be able to receive anything. Okay, and we have some calculations here to show how much isolation we need, right? So the way we arrived at these calculations, let us say you get some isolation. So which isolation am I talking about? I am talking about the power received here. You have some isolation here, right? Some amount of self-interference, so from your own transmitter into your receiver, is leaking through here through the duplexer. This is not ideal. This power, you can put a spec on it, very easy. Let us say you say this should be below the noise floor, right? Then the transmit signal gets buried under the noise floor, right? It looks as if, the noise floor might increase, but you can say that it should be less than the integrated noise power. So you integrate the noise power over the band, you assume it's broadband noise, integrate the noise power, say it should be lower. So for example, if you take a, for wireless LAN, the integrated noise floor is about 190 dB below the TX signal. Yes?
So just one question. In the previous slide, the slide before this,
yeah.
You mentioned the last point you said if not suppressed it can saturate. You mean due to lag, because there's non-zero self-interference, that power leaking through could saturate the receiver?
So what happens is the receiver is meant to process signals which are at minus 80 dB, minus 70 dB and so on, at dBm and so on, all the way up to maybe minus 30 dBm. Okay, not more than that. Now, if you take such a receiver which is designed to handle very small signals and give it a combination of such a small signal and such a large signal, it will pretty much respond only to the large signal. That large signal will push the circuit into its nonlinear operating region, which is normally saturation. Your input power is so high that it will just be saturated. You will not get, at that point you won't get any gain out of the system for any small signal that you apply on top of this large signal. That is what I mean here.
Okay.
When I say it saturates.
So the idea is that block you put in the middle, that has to now reduce how much of your...
Exactly.
But that's not perfect, you're saying.
It's not perfect.
Okay.
So ideally it would, the isolation self-interference would be 0, minus infinity dB. Then the system remains exactly the same. That's not going to happen. Okay. Now self-interference, you can say, hey, I may want just enough self-interference to push it into the linear region. But even that is not good enough. Even that is not good enough because you want to ideally push it below the noise floor so that there is no degradation in the performance. Okay, so imagine trying to, get some usable signal when there is some other large signal riding on top of it. Even though the processing circuitry is linear, you will need to burn extra power, signal processing, etc. to extract out the desired signal, assuming that you can separate it out. Okay? Any other questions? Okay? So, if I put the TX signal exactly at the noise floor of the receiver, right? The effective noise floor, they are uncorrelated. So, in modern communication, your received and transmitted signals are all broadband signals, right? They are OFDM modulated. they will look like noise floor. They are all spread in some way or other. They will look like any other broadband noise floor. There is no correlation between the transmit and receive signals, so it will look like the noise floor is being raised, right? And if you equate this, the TX power, leaked power to the noise floor, it will look like your noise floor has gone up by 3 dB. You add it in mean squared form, noise, right? It will look like the noise floor has gone up in 3 dB, by 3 dB, right? If you do not want the noise floor to go up, the self-interfering signal from the TX, the leakage signal, needs to be maybe 10-15 dB below the noise floor, so that you only see some, half a dB or 0.3 dB, something like that. I hope that makes sense to everybody. Okay? So, if you want to push it by about 11 dB, you need about 130 dB. Right? The lesser degradation you want in the noise figure, effective noise floor of the system, the more self-interference you need. Okay? So now, if you see broadly, the way to combat this self-interference is broadly by 2 ways. One is by suppression. You don't even allow the interference to reach the receiver. That is the 2-port block, right? But once it has reached, so you go back to this block diagram. So you try to build this such that this power leaking through is very small. But once some amount is leaked, you also want to be able to cancel it. The good thing is that this is your own transmitted signal. You know it perfectly. In an ideal world, you know it perfectly. You can make a reproduction of that. You should be able to cancel it. That is the idea. Okay?
So would
Yeah.
one just try to directly cancel it right there? In that-
Where here?
No, in the block in the.
This one?
Yeah.
Actually, that's what you don't need to cancel it. You need to channel that power, all the power into the antenna. There is no cancellation required.
Okay, right. Whatever.
If all of this power went into the antenna, you have done your job. No power will leak through. But this block needs to be perfect, and that's just not possible. Okay? That's just not possible.
Cancellation is done in the RX.
Yes, so suppression is done in this block. Cancellation needs to be done right here at the beginning of the receive chain. You need to do both to achieve like something like numbers like 130. In fact, you can't even reach 130. You will see, right? Numbers like 130, you can't even receive it here. What you can hope for, you do some amount here. You will need to do like a graded way of doing this. You do some amount, some isolation, okay, some cancellation here, some cancellation down inside the RF chain, some cancellation down in digital baseband through signal processing techniques. You need a combination of everything to get 130 dB. Okay, and you will see why. If you look at the implementation in the circuit level, you will see why. Yeah.
So what is that 119 dB?
So what I have said is, okay, this is the integrated input preferred noise, right?
Of the receiver.
Of the receiver.
Okay.
The transmitted power is 20. That happens to be minus 99. The noise floor is minus 99.
Noise floor is minus 99 dB.
Yeah.
Okay.
And this transmitted power is plus 20. So the dynamic range is 119.
Yes.
Right?
Yes.
And so if you cancel it by the transmitted, the dynamic range, if you cancel it by cancel or isolate the TX signal by 119 dB, the TX signal will be exactly at the noise floor. If you do under 11 dB, it is minus 130, the degradation of the effective noise floor will be even smaller.
Okay.
Okay? Okay? How do you achieve this isolation? That block there. Actually, that block doesn't need to be a real block. You can just separate out the antennas. This was the first idea from the Stanford team that implemented this. The first idea was, why even do this? You try to get isolation through the air. Right? You don't need to develop circuits. You just separate, use one antenna for RX, one antenna for TX.
Spatial.
You get spatial isolation. Okay? Now, the spatial isolation, just like anything else, depends on the distance. The further away the antennas are, the higher the isolation. Okay? What happens is that, of course, the isolation is a strong function of distance, number one. But if you also look at the types of receivers that you're trying to build, they are all not very big. So you imagine, I am trying to do this for wireless LAN. Okay? You take a typical wireless LAN router, how big it is? Probably like half a foot, right? You can put one antenna at each end, that's the best you can do. You can't do much better than that. So you will only get like 20-30 dB, you cannot get a lot from that, from spatial isolation. Okay? Then, the next step, of course, this depends on D, whether you are able to physically do this. But the next step, somebody thought, hey, you are anyway using two antennas, why not use a third antenna? Okay, now if you use a second transmit antenna, so now what you do, you take half the power, send it to one antenna, take other half of the power, send it to the other antenna. Okay, now if you remember, the electromagnetic wave in space, it has nulls, okay, depending on the wavelength. So every wavelength it repeats, right? At half wavelength you get the negative of the signal. So if you place two antennas, TX antennas, such that the RX is distance D from one and D plus lambda by 2 with the other, you will get a null. Okay, there will be an extra additional phase shift from 1 of 180 degrees. Okay, so these two will destructively interfere. These two will destructively interfere at the receive antenna. Okay, now just one point, this is also extremely narrow band. Okay, of course, anything related to lambda, you will get exactly 180 degrees at one frequency, right? And if you want like 100 megahertz bandwidth, then now this will not be a excellent cancellation. You may get only 20-30 dB again, same problem. Okay, and then you also need to fit in a third antenna here. Okay, people have also thought about changing the polarization of the antenna. Okay, you can now orient the antenna differently and get isolation from that. Okay, transmit and receive antennas can be polarized differently. Okay, so whole bunch of things are possible. Okay, but obviously,
So that spatial, you said, depends on D because of the 1 by R square.
Depends on because of the 1 by R square.
So
Absolutely.
That is in free space, right?
That's in free space.
People not try putting a material around it which will allow the radiation only in a particular direction and kill it.
You can do it, but you almost always want in mobile devices, you almost always want isotropic radiation. The minute you direct radiation, you will now have to point the phone or point your laptop in a certain way, so you don't want that, right?
So also another question I have, at least with the A solution,
Mhm.
considering that both like TX RX are on the same device, you anyways have to have your TX send it to a phone, say a couple of meters away, whatever.
Mhm.
So that distance D is going to be fairly pathetic in terms
No,
of attenuation.
this TX and RX is your own transmitter and receiver.
Right.
Correct. So
So-
this has nothing to do with where the remote.
Right, sir, but I'm saying now that TX is supposed to send information to
Somebody
another
else.
device, whatever.
Correct.
It will unwantedly also send it to your RX.
Correct.
You don't want, but
Correct.
considering that it's strong enough to send a signal to, say a couple of meters away,
Yes.
the attenuation you get from that D is going to be very less, right?
Actually,
It's on the-
surprisingly, no. You do get enough. You get about 20 dB. So if you move it about maybe a foot away, right? Foot to foot and a half away, you easily get 20-25 dB.
Okay.
Okay,
So
you
then,
easily get 20-25 dB isolation.
So okay, that would inherently mean that the receiver on the device far further away has to be more sensitive then, right?
Actually, these systems are designed. See, the typical range of a wireless LAN system, right, is meant to be about 100 meters, not more than that. Okay. These antennas, the transmit antennas, will put out 20 dBm into free space in all directions, right? If you go 100 meters away in open space, I'm not even talking about with blocks, with walls and so on, in an open field. If you go 100 meters away, you will probably get, the way these numbers are designed inside the standard, most likely you will get something like minus 80 dBm, minus 90 dBm, something like that. That is how they get the sensitivity numbers. They actually measure how much isolation, how much attenuation you get in free space. Okay, based on the range, they will set the sensitivity numbers. Okay, so these numbers, that you get for your, see, what you are saying is true if the remote receiver was only a couple of meters away. If it's 100 meters away, you do have a problem, because you will have to put out max power on this, because you expect that person to receive min power, and that here you will receive min power from that remote receiver. You do have a problem.
Yeah.
Right? In that situation you have, and all these standards are written such that you have to hit the extreme condition.
Yeah.
Okay? Okay? By the way, So in fact, the first work I'm going to present, I've not even come to the work, right? So this is all background material. But the first work that my MS student Gaurav did was to do for such a system. Okay, for a 2 antenna system. Okay? But then what people want is for a single antenna. They don't want to build it for a 2 antenna system. So for a 2 antenna system, you can't use multiple antennas. You need a 3-port element. Like I told you, this is a circulator. Okay. There is a TX port, RF port, and an antenna port. This uses a specific type of ferrite nonlinear material such that you get low insertion loss from here to here, low insertion loss from here to here, but excellent isolation from here to here. But what does excellent mean? You'll get about 20 dB. Okay? You get about 20 dB, not much more than that. And that is purely just on amplitude. The minute you look at the phase response, over 20 megahertz, it will change by 10 degrees. That is kind of, cancellation works by cancelling both amplitude and the phase. You have to match both. Okay, so if you look at this, it's actually not a very well behaved system at all. Okay, if you need to do cancellation. The other way to do it is to try to build a 4-port system. Okay, the TX is basically going to try to split in 2 different ways. You try to match the impedances here such that at least half the power goes into the antenna. Okay, you suffer a 3 dB loss in TX power, which is still okay. So there is a loss in TX efficiency, but you get some isolation. This is called a hybrid transformer. Okay, based on electrical balance. Basically, you try to balance 2 parts and try to get a null in the receive port. Okay, so if you are able to equate this impedance to the antenna impedance, you will get a null here, the receiver. That's the basic idea. Okay. Of course, if you look at the size of the circulator, I say they're bulky. It's not like it's this big, but compared to an IC, of course, it would be big. A circulator would maybe be 80% of this adapter size, right? So let me see. Probably the size of a plug, of a 3-pin plug, right? It will be something like that. Okay, so it's definitely big enough to be noticeable on a printed circuit board if you were to build this system.
Sir, how is a ferrite core incorporated in an IC?
It's not. This circulator is a standalone element outside the IC.
Okay.
It is at the antenna, so you can't. And that's the other problem. You can't incorporate any ferrite cores in your semiconductor process. So there's no concept of integration with an IC. So it's outside.
So the idea at least, sorry, the idea for the B part is you're saying the impedance looking down into that parallel RC.
If these two are equal,
right,
then the power will split equally.
Okay.
You will generate equal voltages here, and if you take the differential voltage at the Rx end, it will be 0.
So would that not be narrow band then? Like I'm not sure the impedance.
Of course, it will be relatively narrow band. It is very hard to build a wide band system. There are various reasons for it. For example, the transformer itself may be narrow band. This impedance of the antenna may be narrow band. Matching it with a simple RC may not be possible. If you do a more complicated network here, you might be able to match it over a wider band. Naturally, there is a limitation. Okay, all of these systems will suffer from some limitation or the other. Okay, so the second type of work builds on something like this, not exactly the same, but something like this, electrical balance, using for a single antenna full duplex system. Okay, now just wanted to say, so this interface we saw, it could be antenna based, it could be circulator based, it could be some balanced system based. Okay, now, so you will need to match amplitude and phase. Okay, now, or if there is a delay, time delay, you have to match amplitude and delay, not just phase, quite possibly. Now, there are also other issues. I am not even touching upon the real practical issues. For example, you imagine a router is going to be placed on a table or near in a wall or on a desk or something. It's going to go out from the antenna, get reflected by the wall and come back right here into the receiver as a delayed version. What do you do about it? What we are talking about has nothing to do with delays. We are talking about leakage signals, creating replicas. How do you generate a system that creates a replica, a delayed replica, right? So if you look at these cancelling path signals, they can get very complicated very quickly in a practical system. Okay, you need probably a filter, a cancelling path filter with like maybe several tens, if not more than 100 taps to match every possible scenario, right? There is a reason. So it may go hit the closest obstacle and come back with very little delay and very little attenuation. Or it may go a little bit further and come back with a little bit more delay, more attenuation. It may go get reflected from a very far away reflecting surface and come back with a lot of attenuation. You need to take care of all of these scenarios. I think Professor Ganti, what he presented would have matched this. How many of you attended, you said? I think many of you attended. He must have covered that aspect in his talk. How to take care of delayed reflections and so on. Okay? Where do you cancel it? A little bit in RF, little bit in analog, little bit in digital. You have to do a mix of everything. There is no way you're going to hit 130 dB. You look at the numbers we're talking about, 20 dB, 30 dB from the antenna based isolation, from circulators and so on. So you can't hit 130 dB in any system. For example, you put a circulator on a PCB, circulator may have 20 dB. Let's say you get a circulator with like 50 dB isolation, just on the PCB through the substrate you will leak 50 dB easily. You will never be able to realize something like that in reality. That's what I mean. So that is why you need it done at many parts, parts in many portions of the receiver. Okay, and these are all numbers. I'm going to concentrate primarily on this. We are going to assume it is done in several places. So we'll assume that digitization can actually give you between 50 and 60 dB cancellation. That is a big portion of the cancellation. Okay, and people have indeed shown that. You will have to use signal processing algorithms to try to separate out the distorted, leaked, delayed copy of the TX, combination of multiple copies of the TX from the received signal that you want to receive. Okay, I hope it makes sense to everybody. Okay, what you do is you assume that you need at least 30 dB in the RF, as much as you can get. Will ease out the others. Okay, so now we come to the first part, right, which is a 2 antenna full duplex receiver, okay, where there is no LNA, the mixer comes right first. I am assuming that at least most of you know the basic structure of a receiver. You have from the antenna, maybe you have some filters, but you basically, the first active component is a low noise amplifier. You need to amplify the received signal as quickly as possible in the receive chain without adding any noise. You try to gain it up without adding noise. That's why you have a low noise amplifier. The mixer happens to be a noisy device and it does frequency translation from RF to IF or RF to baseband. Okay, what does this mixer first receiver architecture look like? Now, the main advantage of this mixer first architecture in a circuit point of view is the fact that you don't have an LNA, right? And these mixer first architectures are based on passive mixers where you just use the transistor as a switch. So it happens to be highly linear compared to an active biased circuit. Okay? You get mixing based on simply the multiplication, passive multiplication you get when you clock the switch on and off. Okay? It also has a fairly wideband operation. You don't have a narrowband tuned LNA up front. The operation of this passive mixer completely depends on the rate of switching, which can be varied quite easily at a circuit level. Okay? It's very compact. There are no inductors, there are no capacitors, it's just a bunch of switches. Extremely compact. You can replicate it if you want, and that's what we have done to take a cancelling signal and cancel it inside. Assume that you create a replica of the transmit signal. You can do that in many ways. You just take a power divider, put it out, you can get a replica at half the power. Okay? So we built identical copies. Okay? So you have an RF input, you have a cancelling input. They both get mixed down. Okay? And then get added in current form, in the form of currents. Current additions and subtractions are easy compared to voltage additions at the input of the baseband amplifiers, where some filtering takes place as well. Okay, that is the basic architecture. How do you clock these? We have a circuit that generates the clock signals. The advantage of this is that any time delays or any phase delays, you can give it through this clocking path to match the time delays. For attenuation, we could have added an internal attenuation, but what we did was we just decided to go with an external 5-bit attenuator on the board, standard component which you can get, very compact, digitally controlled. It's just an attenuator, bunch of resistors with switches. That's all it is.
So
Okay.
the cancelling signal is a replica of the transmitter signal.
Yes. Except in this case, it's also attenuated. The phase response comes from us, but the amplitude response is attenuation happens on the board. Okay.
And RF in is the received signal superimposed with the transmitter.
With the transmit signal, correct.
And this is on an IC or this is on the board?
All of this is on the IC. Okay, so we have the clocking circuitry, frequency dividers, buffers, everything, phase shifters, 2 sets of mixers, 2 sets of baseband, I and Q baseband amplifiers.
RF in what is like the voltage level typically that you can see there?
So the voltage level, okay, so the power level can, for such mixers, can probably go as high as -10, -5 dBm, right? It cannot go, in CMOS technology, it cannot go much more than that, because it can go a little bit higher, but typical IIP3 of these signals, of these mixers, will probably be +5, +10 dBm, and so on, numbers like that. So you can imagine that the compression will start happening about 10 dB below, so -5, 0 dBm, numbers like that.
Sir, what is that input that you're giving to the frequency? I cannot get that.
Here, this one,
Input given to the frequency divider.
input. So all modern mixers, you have both I and Q signals, in phase and quadrature signals.
Yeah.
Okay, because you want to get baseband I and Q signals as well. The easiest way is to multiply with sine and cosine to get both I and Q baseband signals. Now, there are several different ways of generating I and Q LO, local oscillator signals. There are several ways of doing it. You can,
It's just a phase shifter tricks.
no, that is one way of doing it. That's a very bad way of doing it on an IC, because a phase shifter is actually a pretty big block. Okay, this is probably the easiest way of doing it, is to use a frequency divider. It burns a little bit of power, but at gigahertz frequencies it's not a lot. It's a maybe 10-20 milliwatts. Okay, but a frequency divider produces 0, 90, 180, 270 degree signals very conveniently, very easily. Okay, and you build a digital frequency divider using digital latches. You get 0 to VDD signals, which is very convenient to clock, to turn on and turn off these switches.
Okay, so that circuitry is fully digital.
This circuitry is fully digital. Okay, the frequency divider at divide by 2 frequency divider gives you 0, 90, 180, 270. So if you want to operate this at 1 gigahertz, you have to give it a 2 gigahertz input. It divides by 2. Okay, that's what it is.
Yes.
Yeah.
Sir,
Yeah.
how do we change phase response? Let's say we need to match this to.
So we have a phase delay circuitry here. I have a little bit on that. I think in the next slide it's there. There is some, I think on the next slide it's there. But this is the overall schematic of, I'll come to the phase delay. Phase delay is very easy because these are all clock signals. We just put in inverter, I think I have it here. We just did this. Divide by 2. We mux the, the different signals. We delay it using an inverter chain with capacitive loads. We vary the capacitance. It's very easy. It's very easy as long as this thing is coarse. 5 bits or so is 6 bits is okay. Anything more than that, it's very hard. Okay, you can do up to 5-6 bits easily. This is what we did for phase delay. So you can see we got phase step of about 0.2 degrees. Okay, about 12 bits. Now this is at a single point, right? At a single frequency, at a single temperature, single voltage, and so on. If you take into account process variations, temperature variations, etc., this will be, you know, you can easily imagine, but you can get sub 1 degree easy. What does this receiver look like? Like I told you, remember I told you this is just a bunch of switches? This is your mixer. Okay, these are clocked with ABCD signals that is coming from your LO phase generator. That is what I showed you on the next page. Frequency divided plus phase delay signals. Why do you need this resistor? You need this resistor for RF input impedance matching. You need 50 ohms. You need to be this to look like 50 ohms. So you need a resistor. Okay? You need a capacitance because the OTA may be biased not at 0. It will be biased at some common mode. NMOS switches want to operate at 0 volts. They are very good switches at 0 volts. Your input antenna signal is coming from on a 0 volt common mode. Okay, so you put a capacitance here at the output of the switch. Do not mix common modes. Here it is ground, here it is whatever the common mode of the OTA is. This gives you a first order low pass filter. We cascaded, you know, a second one differential to single ended converter with one more set of poles. Okay. Okay. So this is your IC. This is a photograph of the fabricated IC. Okay. And this is all the external stuff that we had to do for testing. Right, connectors, whatever it is, you know, for biasing we have these pots, potentiometers, things like that. Okay, what is the area of this chip? This is about 0.63 millimeters square. Both of these works were done from the UMC Foundry 130 nanometer CMOS process. Okay, FR4 is a very common PCB standard. This is a quick picture of the measurement setup. Okay, so for the LO signal at twice the frequency, you take the RF signal source, send it into a balun, it gives you plus and minus. Okay, so that goes into plus and minus LO. So you take a vector signal generator that generates an IQ modulated signal along with a carrier, modulated with a carrier. So this one will basically generate a real part of x of t e power j omega ct. That's what I mean. Okay, so that is your RF modulated signal. So you put a power splitter, so one of them goes into the input, the other, you know, goes into your other. Okay, and this is the variable attenuator I told you about, which is outside on the board. Measurement results. So if you look at the gain of this, overall gain of this receiver, it's about 45 dB, pretty standard for these types of receivers. Okay, by the way, most of the gain comes from the baseband amplifier. As you might imagine, the switching passive mixer, you don't have an LNA, right? There's no amplification. The switching circuit will not give you a lot of amplification. Okay, so most of this 45 dB comes from the baseband circuit.
OTA.
Yeah, from the OT. From this portion. So you have a current, RF current, baseband current that flows through this to create a baseband voltage here. It's a transimpedance amplifier. Obviously you don't have an LNA, you have a mixer, so noise figure is going to be high. You can see it's a very broadband system. There is no tuning, there are no inductors, nothing, it's extremely compact. And the noise figure is about, you know, maybe 8 to 11 to 12 dB. Anywhere between that. This is expected for such a system. Okay. This is noise figure versus baseband bandwidth. Okay. So measurement was simulated. It's about a couple of dB apart. The integrated noise figure is much closer. It's about 0.7 dB. So what happens is actually it's only about a dB apart, as you can see. If you integrate it over wider and wider bandwidths, you can see 1 over f noise is sometimes not modeled very well. Okay, so your difference between measurement and simulated is higher versus thermal noise flows. That's sometimes common in some processes.
Sir, what is the bandwidth that you're considering?
So For this case, it was 20 megahertz. Okay, about 1 kilohertz to 20 megahertz. Sorry, 1 kilohertz to 10 megahertz. Not 20 megahertz, 10 megahertz. RF bandwidth is 20 megahertz. That's why it's 10 power 7 hertz. This is the input matching S11 at the input of the receiver. So, in general, very good, but you can see that there is a lot of, see what happens is, these kind of receivers, they have not a lot of isolation. So when you are measuring S11, okay, so what happens, these are direct conversion receivers, okay. How do you measure reflection coefficient? You are going to put in some input power here from a network analyzer. You try to measure how much power comes back. The ratio of those is the reflection coefficient. That is S11 effectively as a single port system. Now what happens, the problem with these receivers is that you are going to be putting in the LO. Suppose you are measuring this at 1 gigahertz. You are also putting in 1 gigahertz clock signals here into these switches. And they have very limited isolation. You have 4 of these, you have very limited isolation from the gates of these transistors to the input. You can sometimes see more reflected power than what you put in. It may look artificially like the system is not very well matched. That's why you are seeing these weird peaks in the S11. Okay, in some cases. That is frequency dependent as well. Depends on the package, depends on many different things.
Which band this receiver is actually designed for? For which?
It is designed to operate from maybe a few hundred megahertz to a couple of gigahertz. Okay, there are a lot of cellular bands in this region. Okay, this was not meant for 2.4 gigahertz operation at all.
Because the S11 is resonating at multiple frequencies, so is it not like multi-band something?
This was measured separately at multiple things. You measure multiple bands of frequencies. They did not just measure it in one go. This is not resonance. This is basically S11 as a function of frequency. So this is not resonance.
But there seems to be a resonance at 2 gigahertz.
You are talking about this one?
Yeah.
Yeah, correct. So like I said, the way you measure it with the network analyzer, it highly depends on how much feed through is there from the clock as well as the package parasitics. There is no inductor, explicit inductor inside the chip. Okay, so there is no resonance. Any resonance is coming from the package and not from the circuit. What you're saying is right. Indeed, there seems to be extremely good matching somehow at 2. Okay, most likely because this is a QFN 40 package. It's a pretty large package. So you probably have a couple of nanohenries from the inductance. Okay, from the bond wire inductance, it's resonating with some cap. Okay. This is the self-interference cancellation. How much cancellation do you get? You are putting in so much power, so much power. RFN cancellation input. How much of the cancellation input actually comes out? Right? So it turns out we measured on 3 boards. So somewhere between, let's say, till about 1.2, 1.3 gigahertz, between 30 and 40 dB on the average. Okay? Once you go higher, it starts to degrade a little bit. Okay? Expected. Okay? And you can see some commonalities between some of the boards. You can see they are all having a peak at, like a tip at 1.5. Clearly there is something specific going on there, right? Most likely with respect to the package. Somehow this thing, because the ICs are pretty much identical. They are all fabricated together. There is no reason why they should behave so differently, right? Like between this and this, right? Or across frequencies. This is the cancellation as a function of the RF signal bandwidth. So you are putting in 1 megahertz signals, 5 megahertz signals, 10 megahertz signals, 20 megahertz signals. You can find out how much cancellation you get. Wider the bandwidth, the harder it is to cancel over a wider bandwidth. So obviously cancellation would go down. So if you just use a 5 megahertz signal, you will get about 45 dB cancellation. If you use a 30 megahertz modulated signal, you will only get 39 dB. Okay? If you go to 100 megahertz, it will be like 25 dB or something.
This is just because non-linearity of devices.
it is nonlinearity is one thing, but what happens is we are trying to match any time delays, leakage of various components with a pure phase shift. Okay, the phase shift, so across a wider and wider bandwidth, all components, see your IC components may behave linearly, but other components may not, right? They may have a nonlinear behavior, any packages and other things, they may not have a linear phase response. So this is the measured intermodulation response, okay, before and after cancellation. Okay, so this is the fundamental, this is the intermodulation before cancellation, IM3 before cancellation, this is the IM3 after cancellation. You can see a clear improvement in the intermodulation performance. Of course, because you are cancelling the leaked TX signal, it is looking more linear. With and without cancellation, you can see the gain, significant difference. Of course, it's not saturating anymore. This is the signal to interference plus noise, and distortion ratio. So it's pretty good. Okay, so this is the maximum. Okay, so I'm going to move through this because I want to go to the next one. Right? So far, so good. Simple circuit has a lot of advantage. Right? Great. But now we don't want to have two antennas, right? You want to do it with a single antenna, you don't want to depend on spatial isolation, etc. So we'll see how much time do we have? Huh? You can go until 7. Everybody has the patience? Okay. Okay, so great. I think 7 should be very comfortable. So now, suppose you are doing a single antenna system. Of course, there are various types, of cancellation circuitry that has been demonstrated. But we realize something interesting. So, when you have two full duplex nodes, right? Usually, the data rate is not symmetric, right? Very often, you may want a very high download rate, not a very high upload rate. Right? Situations like that exist all the time. Okay? So, if you have an asymmetric system, right, there is a specific kind of requirement you need. What is that requirement? You need, if you have a high data rate like this and a low data rate on this side, okay, you can tolerate a higher insertion loss because the data rate in this path is low. Your receiver can have a higher noise figure, higher insertion loss, etc. Okay? This is the high data rate path. You cannot afford to have a lot of insertion loss in the transmitted power. Okay, you need to get as much power as possible here. In this side, the requirement is exactly opposite. Okay? So this is the low data rate path. You can afford to send lesser TX power. Okay? You can have more insertion loss in the TX. But the receiver better be really, really good. I hope that makes sense. And this is a very real scenario in many communication systems. Okay, so now what you now need to build a duplexer with controllable insertion loss. So that you can, depending on the data rate, you can just kind of tune the insertion loss of the TX and RX. Okay? And you favor the paths that has higher data rate.
The insertion loss you refer to from TX to.
So here you need, this is the high data rate path. Okay, this is the low data rate path. So in the high data rate path, you need this transmitter to be very good, as high power as possible. This receiver to be as good as possible. Here, you need the exact opposite because the data rate is a low data rate communication. So you can suffer more loss from these two circuitry. You cannot suffer so much loss from these two circuitry. Okay? What I mean, you can have more loss, more noise figure because this is the low data rate path. You cannot have so much noise figure, you cannot have so much loss in this part, right? That's the basic.
But still, why we would need a tunable duplexer? I mean,
How else will you do it?
no, because even low insertion loss is going to favor both, no?
No. Here you need high, you can tolerate high insertion loss,
Yeah, we
but
can
you
tolerate-
need low insertion loss here.
Yeah, we can tolerate high insertion loss, but even if the insertion loss is low, it will not affect the signal.
Correct. But suppose you can see now. Okay. So now let us. I don't want to go back to that full thing. Okay. So if you remember the original diagram, right? Half the TX power was getting lost to get perfect cancellation. Suppose I did not want perfect cancellation. Right? The effective noise floor of your receiver, I can tolerate a higher effective noise floor. Right? But I'm going to favor, so I'll take you back to that slide to remind you of what I'm talking about. I think this is the one. Great. Let me see. You remember this one, the balanced one duplexer? Half the TX power goes here, half the TX power goes here. If in that case these two are equal voltages, then you'll get a null here. That is a perfect case. You'll get perfect cancellation on the receiver. Receiver noise floor does not increase at all. You have lost half the transmit power, right? But suppose I know that my transmit power should be, I cannot handle 3 dB loss in the transmit power. Why can I not do that? Because it's a high data rate communication. So I need to get as large a signal as possible at the remote receiver. I need to send more TX power from here. I need to divert more of the TX power here, less of it here. The resultant is that I'll get a resultant. I will no longer have perfect cancellation through this balanced system, right? Which means my receiver has now suffered at the cost of the transmitter. Does that make sense? So that is the kind of scenario I'm talking about. You can indeed, if you take these systems, what happens is if you try to favor the transmitter, your receiver will suffer, and vice versa. That is what I mean when I say that in the asymmetric link, you want at the cost of one, you are favoring the other, and vice versa.
How are you favoring the transmitter?
I am sending out more power from the antenna. That is indeed favoring the efficiency of the transmitter directly.
But that is the output of the transmitter.
This is the output of the transmitter. I don't understand. This is the output of the transmitter. If I need to send 20 dBm here at the antenna,
Okay.
the transmitter needs to send 23 dBm.
Yeah.
Half the power will go here, half the power will go here.
Yeah.
But suppose I want to send 23 dBm here. What will you do?
You can send it out.
No. You either need to send 26 dBm here, right? Or divert all the power here, so you need to do something with this impedance, right?
Yes, sir.
That's the scenario, exact scenario I'm talking about.
Means we need to intentionally increase the insertion loss of one side so that
You need to intentionally do something to divert more of the transmit power to increase the efficiency, reduce the loss in the transmit power. Okay? So that extra loss I'm talking about is coming from the duplexer. I hope you understand that. The insertion loss I'm talking about is happening inside the duplexer. This is always putting out 23 dBm. I am deciding to divert more here or less there. Okay? At the cost of receiver performance. A very simple example of a balancing system, bridge on bridge. Right? All of you must have seen this, I'm sure. Right? If you want to create a null here, you need to have a certain ratio. R1 by R3 is equal to R2 by R4. Creates a null here. Right? Very simple bridge. I'm not even taking that transformer with the antenna and impedance and so on. A lot of electrical balance system work like this. You try to balance resistors or even impedances at the next level. Okay? So literally that's exactly what all electrical balance duplexers work with. Okay? You build an AC bridge, you balance the ratio of impedances, you will get a null. Now if you tune some of these elements, you will get a variable null, right? The null frequency could change. Okay, you could also change whether you get a null or you get some residual value. You might be able to tolerate a residual value. Okay. So there is a transformer called a hybrid transformer which does exactly this, right? But we don't want to go the transformer way because number one, making a tuning point is bulky, right? So we want to come up with a different tunable balanced system. You don't even need a transformer. You can use a capacitor. Remember, you're just trying to build an AC bridge. There is no requirement to have a transformer or an inductor. You can just use capacitors. And the advantage of capacitors, there are actually several advantages. Capacitors are much more compact compared to inductors on ICs. Easy. Number two, if you want to make it reconfigurable, it's very easy. You want to tune C1, C2, very easy. It's routinely done, believe me, on every IC that you have, that you use in any electronic system. You will have a capacitor with banks. You'll have banks of capacitors and switches to tune something or the other in every analog IC that you can imagine, or RFIC. Okay? You want to tune a filter bandwidth? You need a tunable capacitor. What is the easiest way? You have a bunch of capacitors and switches. Tune it. Right? Easy.
Sir, one doubt.
Yeah.
You said the circulator should consist of non-reciprocal devices.
Yeah.
But there is no non-reciprocity seen here.
Exactly. So in this case, the insertion loss will be at least 3 dB in a balanced system. Right? In a circulator, it is not 3 dB. In a circulator, because it's a non-reciprocal system, you do not burn half the power in the balancing element. Whereas in all of these non-ferrite based linear circuits, you burn half the power. You can't do anything about it. What you can do is around that half, you can tune this way and that way. That's what we have done in this. Okay? Finally, the quality factor at gigahertz frequencies. You take a couple of gigahertz, the quality factor of the capacitors will be like several tens, like 60, 70, 80, numbers like that. Quality factors of inductors will be like 10, 15, 20, numbers like that. So these are much more high quality components. Balancing condition is the same. C2 by C1 should be some factor K. I'm going to call it K, the ratio of the antenna to the balancing. And then of course, we don't want to build a fully differential receiver. We just want to build a single-ended receiver. So we put in a transformer here. Right? You take the balancing points, the null points. It comes as a differential voltage. We convert it to a single-ended voltage and just have a single-ended receiver. Okay? This is a simulated tunability. You tune the cap ratio K, you tune the Z-AND to Z-BAL effectively. What happens is the insertion loss and noise figure will change in some way. So this is just comparing the hybrid transformer with the capacitor bridge, right? There are some advantages and some disadvantages as well. Okay. But if you purely compare the range of Ks and the overall figure of merit, which is basically noise figure plus insertion loss in the transmit side, if you put these two together as a metric, it turns out that the capacitor bridge for a large range of Ks performs better than the hybrid transformer. So that's the whole goal of showing that you can do something better than something that has been done before. Okay, so this is just some target numbers. I'm not going to this thing on this too much, but we basically wanted to hit some numbers like 50, 52.3 dB and so on. So this is the schematic of your receiver plus duplexer. So of course there's no value to building the transmitter. transmitter is coming in externally. It's outside the overall duplexer and receiver. It is just an input. So if you look at this, this is the duplexer, TX port, antenna port. Balancing happens internally. These are the capacitive, tuned capacitor bank. Transformer. It becomes single-ended. You go into a single-ended LNA. I call it a low noise transconductance amplifier because there is an output current. This portion you may recognize. It's a mixer, passive mixer, switch-based mixer. This portion also you may recognize. It's an OTA with resistive and capacitive feedback. It's basically a transimpedance amplifier. Okay, so single-ended current. It goes through these four to create I and Q outputs. Direct conversion DC. Okay.
Sir, is that LNA a differential LNA?
Single-ended.
Then we are receiving a differential signal. I mean,
Where are you receiving? You are receiving actually a single-ended signal only from the antenna. It is getting converted into a differential signal because the null happens across 2 points. I am converting it to single-ended using a transformer.
the transformer is also playing the role of a ballast there.
Yeah. So this is your integrated circuit again on 130 nanometer CMOS. Forget about this area, it's taken up by somebody else's circuit. Okay. The active portion of the circuit is about 0.73 millimeters square. Okay. That includes your duplexer, your transformer performing balun action, differential to single-ended. You have your low noise transconductance amplifier, your mixer plus LO devices, and your baseband filters. Which is the largest? You can see the baseband is the largest. That's always the case. Right? If you have a baseband filter, it's normally the largest. Okay? You can't do anything about it. You need a certain filtering action, you need resistors, capacitors that are going to be large. Okay? Especially if the bandwidth is low, it will be large. Okay? You can see these inductors take up a lot of area. Look at the LOs, mixers, they are extremely small. Okay? Now, of course, the proof of the circuit is in measured operation of the circuit. And this shows the operation from 2.4 to 2.6. Okay? This is the isolation from TX to RX. Okay? Naturally, it's very strongly frequency dependent. Okay? These are a whole bunch of measurements. But the mean isolation is very good, over at 20 megahertz. What you do, you take a 20 megahertz chunk and see what the average isolation is. Okay, you can see it is hovering 55 to 60 dB over this entire band. So you can see it's much better than the previous work. Previous work was about 45. This is doing even better. And this is, 2.4 to 2.5 is the wireless LAN band. What was the other big thing? We wanted to showcase tuning for asymmetric links. You want to bias the receiver over the transmitter and vice versa. And this shows the measurement over various cap bank ratios, the C1 by C2 ratios. So from 0.6 to 1.2, you can see that the noise figure is steadily decreasing when you increase the capacitive ratio. The insertion loss is steadily increasing. If you look at the sum of the two, it's broadly constant. Okay, that's what you want. You want to be able to bias, either increase the RX noise flow or improve the RX cancellation at the effect of TX efficiency. Okay. This is the IIP3 of the circuit. Antenna to TX to antenna, it's about plus 50 dBm, right? So this is of course expected to be very good. Antenna to RX, it's about minus 4 dBm or so, which is pretty standard for these types of receivers, right? Most wireless LAN cellular receivers will require numbers like this for the receiver. This is the frequency response, okay, of the noise figure and insertion loss and gain, okay, for a balanced k equal to 1. So it's perfectly balanced, right? So the gain is about 26 dB. The noise figure is about 7 dB. The insertion loss is about 5 dB. Okay. So if you look at this comparison, so in general it does well. The most important thing about this is the tunability. That's what we were targeting right from the beginning. So for a modern type of communication link where you have asymmetric data rates, you need that tunability, and this is actually, I think, may still be the only work or one of a few works that shows tunable insertion loss, noise figure of the receiver for a full duplex system. Why does it have a fairly large noise figure? Because the balun which you use to convert from differential to single-ended happens to have loss. That loss directly adds to the noise figure of the system. Okay, if we had decided to forego that balun and just use the differential LNA, we would have burnt more power. Okay, double the amount of amplifier LNA power, but we would have been able to make it much more compact, right? As well as have much lower noise figure. Okay, but we might have had to live with common mode leakage. That will depend on the CMRR of the LNA. Okay, if there is any leakage through the common mode. So what do I mean by common mode? So here, if there is any leakage capacitively between turns from the primary to the secondary, that is a common mode leakage. That's a physical leakage. Okay, you can't do anything about it except hope that that leaks to both LNA, differential LNA ports, right? And it cancels through the CMRR of the LNA. We don't know if typically so-called differential LNAs are normally pseudo-differential. They are not truly differential LNAs. Okay, so it's hard to imagine that would have worked out well. Okay, so now I just have a couple of slides and then I'm going to stop. Okay, so I've kind of shown you two big works, but I just want to show you what the future work. Yeah, yes.
So the antenna pads, you remove the EEA diodes and all that stuff, is it? Basically to allow high frequency signals to come in and all that?
No, what we did was we made our own custom ESD structure, which was much smaller capacitance. We took their ESD structure, made it a much smaller diodes. We cut the diode sizes by like 1/10 or even more I suspect. That's what everybody does, by the way.
Okay, that's what I was
You can't, yeah.
Don't remove it, right?
Absolutely, you can't remove it. You can't remove it. Okay, so we made something much smaller. By the way, everybody knows what ESD is, right? People tend to pick up static electricity, right? And picking up static electricity of several hundreds, if not thousands of volts is very common. Okay, if you just touch something, you can zap, you can transfer charges that can break down, transistors, capacitors, and so on. Okay, very easily. So normally what happens, there is protection circuitry on every IC. Okay, that will normally be diodes that will turn on to conduct current, turn on very fast. Okay, to bypass current to VDD and ground so that you don't hurt the gates of the transistors.
They reverse bias.
They are reverse biased during normal operation, but if there is any spike in the positive and negative direction, they will turn on immediately and conduct all the current, all the charge to VDD or ground. Okay. So normally, if you look at baseband circuits, digital circuitry, etc., everything needs it. By the way, you need ESD at every point where there is a transistor connected. Okay. Now what happens? The ESD diodes that come up are typically have capacitances of a few picofarads, couple of picofarads. Okay, it may be fine to put on baseband nodes 20 megahertz, couple of picofarads is going to do nothing. Okay, if you have a 20 megahertz digital signal, nothing. If you have a 1 gigahertz digital signal, a clock signal, you have a problem. 2 picofarad is a lot of capacitance. You'll have to burn a lot of power, right? Your rise time, fall times will go bad, and so on. Similarly, any RF inputs, you have a problem. Okay, you can't handle, you're trying to operate this at 2.4 gigahertz. You just cannot tolerate capacitances like 2 picofarad or 1 picofarad, right? The capacitance that you can probably tolerate is maybe 100 femtofarad, something like that. So we had to build our own custom structures, ESD structures, which will, obviously that means making the diode smaller. Automatically, the diode that was capable of bypassing current of the order of, currents for ESD discharges of several thousands or couple of thousands of volts will now only work with couple of hundreds of volts to make it 1/10 the size. But that's still better than nothing. Okay?
So you did it for reducing the capacitance.
Yeah. So the circuit shown here does not show the ESD structure.
Yeah.
Every external pad will have an ESD, couple of ESD diodes hanging. They will have a couple of picofarads. Your circuit is short. If you try to hang 2 picofarads here, your circuit just won't work anymore. Okay? So, I just want to give you an idea. I don't have more than a slide or two on this. What is the future of full duplex? Well, I think Professor Radhakrishna must also have covered this a little bit, but really there is a lot of potential, but you can see the circuits get very complicated very quickly. So there is still a lot of work to be done to simplify these types of full duplex systems. If you do that, there is potentially a lot of advantage to doubling spectrum usage, number of users, etc. And there are several several possible ways. For example, people have done work using polarized antennas. One of the things I showed you right at the beginning. You get some isolation if you polarize the antennas differently, right? They don't need to be spaced apart. Okay. Now the next question comes: what happens if you place such polarized antennas in reflective environments? What does that look like? How much cancellation should you expect? Second thing, modern wireless LAN receivers are not single channel receivers. You have a minimum of 4 channels in any modern Wi-Fi router that you buy, or your Wi-Fi on your phone. They are all like typically 4x4. Okay, because the kind of data bandwidth that you need, right? You need that kind of number of IOs. So now imagine we did a 1x1. Imagine a 4x4 full duplex system. What does that mean? I have 4 transmitters, 4 receivers. Every receiver will get the a linear combination of 4 transmitted signals. You now need to create a cancellation signal that is a linear combination of 4 TX signals. Each one of them having a unique signature, unique amplitude signature, unique phase signature. Not trivial at all. Okay, so lot of work to be done in building that. There are some initial, very high level ideas, but lot of work to be done. Next thing, all of this, both the works that I have shown, we are only putting in a single defined x of t. Okay, we have tested it with an antenna in a shielded room where you have no reflections. If you put it in the real world, like I told you, you will get copies of tx, various amplitudes, various copies, various amplitudes, various delays. Okay, so you not only need to calculate x of t, alpha 1 x of t minus tau 1, alpha 2 x of t minus tau 2 plus alpha 3 x of t minus tau 3 and so on. Okay, that is the actual signal you need to cancel in the real world. Okay, now Professor Ganti has done some very interesting work on how to do that, right, at baseband. Assume that your RF processes this very well. You can actually cancel a significant portion of it in baseband by implementing some very nice algorithms.
That are purely digital algorithms.
Purely digital algorithms. Okay, in very nicely it is. See, many of these nice ideas are actually very simple ideas in the sense that they go back to some fundamentals. Like some of the things that he did, you can actually expand this in a Taylor series. A delayed signal, right? You can expand it in a Taylor series. Okay, now what you need is a filter with the Taylor series coefficients. So now that happens to be relatively easy to implement in digital, right? With some relatively, for example, we did it in an FPGA. Okay, with a medium performance FPGA, you can implement it. Okay, now the next question is, can you actually cancel these reflections at RF? You now need to build a multi-tap filter at RF. Okay, so you need to generate multiple copies with various attenuations, various delays. Okay, and cancel it right at RF. So these are all, I guess, potential for research in this area going forward. Okay, people have done some of these in some way or the other. Okay, so anyways, I think I have one slide on each, but I think you can keep talking about this, but I'm kind of going to conclude here. Okay, so broadly, I talked about full duplex systems from the system level, what you need from duplexers, why you need duplexers, what you need from these duplexers. Then I presented two pieces of work. One is from my MS student Gaurav Agrawal, the other is from Abhishek Kumar, the second one. The first one was a 2 antenna system, the second one was a 1 antenna system. Okay, and both of them were implemented in 130 nanometer CMOS. Measured results look largely correlated with the simulation results. So that's a testament to the attention to detail that the students put in, right? And finally, I pointed out that there is a lot of scope for research, right, in full duplex systems. And this is going to be like a candidate for the 6G standard. They talked about it for 5G, but 5G already had many challenges. So they kind of paused it. During the early days of 5G, they talked about it a lot, but they paused it. Now that 6G is coming up in a few years, the standard needs to be started up, standard discussions in a couple of years. They have already started looking at full duplex, okay, as a candidate for 6G, as one of the candidates for 6G. Okay, so I'm going to end my talk here. Thanks to E2A for inviting me to give this talk. I'm always happy to present my students' work. It is their work, right? Obviously, they did most of the hands-on schematic design, layout, testing. Everything is done by the students, right? We are happy to discuss with them, come up with ideas, help them solve problems along the way. Okay, so thanks.
You said you cancel across the baseband, the RF and digital, right? Is it for efficient power purposes you do this, or is there fundamentally something that says you have to do it all?
Yeah, so if you look at any RF cancellation, it is going to be highly narrowband due to various reasons. The antenna characteristic is narrowband. Okay, so it does not have a very broad, it has relatively narrowband characteristics, especially if you go beyond 100 megahertz. There are normally front-end filters that have very strong narrowband characteristics. The LNAs that are used are normally tuned LNAs. Okay, all of these put restrictions on the amount of cancellation you can get for a wideband signal. For a narrowband signal, if you tell me the signal is only a 1 megahertz wide signal, you can get very good, you can get 75 dB, right? The minute you start going to 20 megahertz, 50 megahertz, 100 megahertz, the amount of cancellation starts coming down from the RF, because matching especially the phase characteristics over such a wide band becomes extremely difficult. Okay, so even the circulator gives you 20 dB, okay, cancellation. Now, if you had a 20 dB lower signal with very well behaved, let's say a flat phase response or a linear phase response, that's okay. But if you look at the phase characteristic, right, it is highly nonlinear, okay, over 100 megahertz bandwidth. So which means the circuit that you need to compensate for the circulator leaked signal just got more complicated. Okay, so which is why the amount of cancellation you can get at RF is limited. Okay, if you're talking about wideband signals. Okay, I can't imagine getting more than 50 dB, 55 dB at RF, unless you want to burn a lot of power and make it, very complicated. Okay, which is why the steered approach of doing a little bit at RF, little bit at baseband, little bit at digital makes sense. Now the problem with it is that if you do it at RF, you have access to the transmitted signal directly. If you try to do it at baseband, you have one of two problems. Either you take the TX signal from baseband itself and try to cancel, which means you miss all the nonlinearities of the transmitted path. You will never be able to cancel it perfectly. You are trying to create a perfect replica, whereas the TX path itself has imperfections. Otherwise, you need to have a second receiver, right, which can give you, take the TX output and give you a replica at baseband. Now you need to worry about the imperfections of that second receiver. You can never win. Okay, that itself may have a leakage. Okay, you can never win. Okay, so you need to do a tiered approach. Okay, you cannot get all cancellation at digital for sure because the receiver will never be able to handle. Right, which is why this tiered approach makes sense. Any other questions?
So, efficient signal processing algorithms, right? So that can be implemented using some ASICs or something.
Yes, it can. Absolutely, it can. Depends on where you're doing it. If you're going to do it on a mobile, it needs to be an ASIC. If it is, for example, on a base station, cellular base station, they already nowadays modern base stations, 4G and 5G base stations very often have an FPGA. So you can implement it on an FPGA. But having an AC core will probably make it better. If you're going to put it on a wireless LAN router, you'll definitely need a ASIC. You're not going to put an FPGA on a wireless LAN router. Okay? Unfortunately, you know, building an ASIC for the baseband processing algorithm does not have, it has a lot of value if you're building a product. If you're showcasing research, it does not have a lot, it's a lot of effort. Okay? It's a lot of money to get it fabricated. It's much easier to show it on an FPGA in real time. Any other questions?
Okay, so then, so let's thank Professor Aniruddhan for this wonderful talk. On Saturday, I listened to this talk by Professor Abhishek Kumar from IIT Hyderabad. This student, unfortunately, only 10 minutes, so I couldn't understand almost. I understood almost nothing. So I was more than happy to attend this talk. Nice, slow, detailed talk. So it was a great one. And thank you.
Thanks a lot. Thank you.